All right, so this is the last chapter of Math 30-1, dealing with permutations and combinations. Basically, it's determining how many ways things can be arranged, is really what it boils down to. How many ways can things be organized? How many ways can things be chosen or picked? That's basically what we're going to be talking about for the first part of this chapter, and then we're going to get into something called binomial expansion, which we'll see is connected to counting. Okay, and what binomial expansion is, it'll give you a pretty systematic, quick way to expand any binomial raised to any power. For example, 2x plus 3 all to the 10th. Instead of multiplying it out 10 times and doing that, we're going to see a way that that can be done, and it's fairly quick. And you can do the whole expansion in probably 3 minutes of 2x plus 3 to the power 10, or any binomial raised to any power. Okay, so that's what we're going to be talking about in this chapter. But first, again, we're talking about how many different ways can things be arranged or chosen or picked. So let's see if this works.
If you only list your vacation home on Airbnb, you might get a few people. But if you also list it on Vrbo, you'll get Vrbo families who...
I don't know how to get rid of this thing on the side. Okay, well, I guess we don't get to watch the video. So all it is just an old guy standing behind people at a checkout at a store, and he's trying to watch them put in their PIN number. Is what it is. So if you were trying to guess someone's PIN number, how many different 4-digit PIN numbers are available for bank cards? So we're going to learn how to determine what the answer to that is. That'll be part of this chapter. How many different test responses are possible for a test consisting of 10 multiple choice questions, each with 4 possible answers? So if you're guessing at every one, how many different possible sets of solutions could you provide? So we're going to learn about that. How many different QR codes are possible? So these are all examples of types of questions that we will learn about as we go through this. How many different license plates are there? If you can have any 3 letters followed by any 3 digits, and let's say there are no restrictions on which letters or digits you may use, which is actually not true. When you're doing license plate, there are restrictions on what letters a person could use if you're choosing your own license plate. Okay, so we'll learn about how we deal with examples where there are restrictions, certain things from a set that cannot be chosen, how we deal with those. So in this unit, we'll be studying a branch of mathematics called combinatorics. It's a branch of discrete mathematics, can be defined as the art of counting. There are some famous combinatoric problems, including something called Pascal's triangle that we will use when we do our binomial expansion. Something called the magic square, this Konigsberg bridge problem, Kirkman's schoolgirl problem, and the Miriorama cards. So you may have heard of some of these, maybe not. But these Miriorama cards were invented in France around 1823 by Jean-Pierre Bray and further developed in England by John Clark. Early Mirioramas were decorated with people, buildings, and scenery that could be laid out in any order to create a variety of landscapes. One 24 card set was sold as the Endless Landscape because there were so many different possible ways that could be laid out. How long do you think it would take to generate the 6.2 times 10 to the 23 possible different arrangements from a 24 card Miriorama set? So that is how many different possible landscapes or arrangements of those cards that could be set out. 6.2 with 22 zeros after it. That's a huge number. So we'll learn where that number comes from. Another thing we'll learn is we'll see how many different possible tickets you could buy if you wanted to buy a ticket for every possible arrangement for Lotto 649. We'll learn about how we can figure that out, how many different are possible. So let's start this. You just want a trip to San Diego for the weekend, but you can only take a carry-on. You pack 3 t-shirts, a black, a gray, and a white one. You pack 2 pairs of shorts, a red and a white one, and 2 pairs of sandals, 1 black, 1 gray. How many different outcomes are possible? So you might make a guess. How many different outcomes you think might be possible if you have 3 shirts to pick from, 2 pairs of shorts, and 2 pairs of sandals? One way to get the answer would be using what's known as a tree diagram. So you would start first, we've got our shirts. And the possible colors for shirts are black, gray, and white. Then you have to choose what color of shorts you want. And for every different shirt that you choose, you have 2 choices for shorts. You have a red pair and a white pair. Has anyone ever seen a red pair of shorts that actually look good? Okay, maybe the guy's colorblind, okay? So for every shirt that is chosen, there are 2 choices for the shorts. And so if we just stop there, right now we have 6 different possible outfits that could be chosen. If you choose a black shirt, you can either have red or white shorts. There's 2 choices right there, 2 combinations, 2 outfits. If you choose gray shirts, again, you have red or white shorts. There's 2 more different outfits. So now we have a total of 4, and then the last 2 gives us a total of 6. But we're not done because now we have to choose our sandals. And for every choice of shorts, either red or white, we have 2 choices for sandals, black or gray. So I'll put BL for black and then G for gray. BL for black and G for gray. For every choice of shorts, there are 2 choices for sandals. So now we see there are 10 different outcomes. Some of you may have guessed that. Sorry, 12. 12 different outcomes. That's true. If you don't mind wearing odd shoes, there'd be more. So we'll learn about that, right? What if there are restrictions? That would be an example of a restriction. So we'll learn about how to deal with those. But assuming that he will choose at least 1 pair of shirts or 1 shirt and not eliminate 1 for choices of color or favorite colors or whatever, he'll choose any of the 2 shorts, any of the 2 sandals. There are 12 different outcomes that are possible for this example. Now, the question is there an easier way to do that without drawing the tree diagram? So if you look at this, there are 3 possible choices for the shirts, 2 possible choices for the shorts, and 2 possible choices for the sandals. What could you do to those 3 numbers to get 12? Obviously multiply. 3 times 2 times 2 does equal 12. So there is an easier way to get that number. And this is known as the fundamental counting principle. If one task can be performed in A ways, a second task can be performed in B ways, then the 2 tasks can be performed in A times B ways. And you're not just restricted, obviously, to only 2 tasks. There's no restriction on how many tasks you can combine. We just did 3 different tasks if you want. Those tasks are choosing each item of clothing. So, for example, a restaurant meal consists of one of 2 salad options, one of 3 entrees, one of 4 desserts. So there are 2 times 3 times 4, or 24 possible meals. This is the fundamental counting principle. In a Math 30-2 quiz, there are 8 multiple choice questions. Each question has 4 choices, A, B, C, or D. How many different sets of answers are possible? So when you're using the fundamental counting principle, you might start out by putting down a blank for each different event. There are 8 questions here, so we have 8 events. In the example we looked at with choosing an outfit, there were 3 events: choosing a shirt, choosing a pair of shorts, and choosing a pair of sandals. Here we have 8 events because there are 8 questions. And for each question, you have 4 possible choices. So the answer to this question will be found by multiplying 4 by itself 8 times, or 4 to the power 8, which is a pretty big number, 65,536. So if you were guessing at every question, that's how many different possibilities you could come up with. So you can see that if you're guessing at every question, the chances of doing well on the quiz is not very good. Example 2, an online game has asked you to create a password. It must be 4 characters in length, and you may use any lowercase letter, any uppercase letter, as well as any digit to create your password. So there are 26 letters in the alphabet, which means there's 26 lowercase, there's 26 uppercase, and there's 10 digits, 0 through 9. So that gives a total of 62 different choices you have. Again, it's going to be 4 characters long, so if we put down 4 spaces, and there are 62 choices for each space. And the fundamental counting principle says that we always multiply these numbers together. So we could simplify that expression and say it's 62 to the power 4. And if you use your calculator, still a big number, 14,776,336. That is using repetition because there's 62 choices every time. But that's what the next question is asking. What if you're not permitted to repeat any character? So you're still choosing 4 items, but there's no repetition allowed, which means you'd have 62 for the first choice, but whatever character you choose cannot be chosen again. Now there's only 61 for the second choice, and then 60, and then 59 for the last. So now we're getting into an example where there is a restriction there. The restriction here is that there's no repetition. And so for right now, the only way we can do this is by putting each number in individually. We will learn about a shortcut, though, that could be used for this. So it does cut down the number of possible outcomes. Now we're only 13 million. 13,388,280. Number 3, determine the number of distinguishable four-letter arrangements that can be formed from the letters in the word English if first there are no restrictions. Well, again, you're only going to arrange 4 of the 7 letters. There are 7 letters to choose from, but you're only going to arrange 4 of them. So you would have 7 choices for the first letter, and then 6, and then 5, and then 4. Think of this like a Scrabble thing. Once you choose a letter, it can't be chosen again. But once you choose a letter, it can't be chosen again. If you write the letters of the word English out, once you choose a letter, you're striking it off. It's gone. Can't use it again. Think of it as a Scrabble. So back to the calculator. 840. So now we'll look at some possible restrictions. What if the first letter must be the letter E? You're still choosing 4 letters from 7 total, but in this case, the first letter is chosen for us. There's only one choice for that first letter. It must be the letter E. So the 1 represents the fact that there's only one choice. We started with 7. If the E's already been placed, now you only have 6 choices, and then 5, and then 4. So 6 times 5 is 30, times 4 is 120. 120 arrangements if the first letter must be the letter E. Now, the next one is similar. The arrangement must contain the letter H. We're going to see that there are actually 4 different possibilities that we need to look at. The first possibility would be if the H is in the first position. However, the H could be in the second position, the third position, or the fourth position. All it says is that the arrangement must contain the letter H. So if it's in the first position, our next will be if it's in the second, our next will be if it's in the third, and the last if it's in the fourth position. Meaning there's only one choice in each of those scenarios for that position. But the remaining positions, just like question B, will be 6 times 5 times 4, which is 120. That's going to be the same answer for the second scenario where the H is in the second position. There's only one possibility for that second position. We're saying the H is there. There's our 1. But then there are 6 for the first, times 5 for the third, times 4 for the fourth. That still gives us 120. You're still multiplying the same 4 numbers together. And that's going to be true for the other scenarios as well. You're still multiplying the same 4 numbers together. The order might change, but you're still multiplying the same 4 numbers together. And so in this case here, you're going to have 4 different scenarios, each having 120 possible outcomes, and now you'll add them up, which will give us 480 possible outcomes. So all the examples we've looked at so far, if you think about it, we're using the word and, right? If we look back at question A, you have 7 choices for the first letter and 6 choices for the second and 5 choices for the third and 4 choices for the last. And means to multiply. But in this last example, we've also included the word or in there. You can have an H in the first position, which is 1 choice for the first and 6 for the second and 5 for the third and 4 for the fourth. So that and means you're multiplying. Or you can have an H in the second position, which is 120 ways, or H in the third position, or H in the fourth, or means to add. So we're going to see this coming up over and over again. If you're using the word and, you're multiplying. If you're using the word or, you add. Question D says, what if the first and last letters must be vowels? So we mark down our 4 spaces. Our vowels are A, E, I, O, U, and Y. In this case here, there are only 2 vowels, the E or the I. So it doesn't matter whether you place the first one or the last one as your first number. Doesn't matter. But let's use the first one. You'd have 2 choices there, either the E or the I. And once you've chosen one of them, you can't choose it again. So that means there'll only be one choice for the last position. You always deal with restrictions first. So our restrictions here is that the first and last letters must be vowels. You could have said that I have 2 choices for the last position, which would leave us with 1 choice for the first. It's not going to change the final answer. You're going to multiply by a 2 and a 1. We started with 7 letters. We've already placed 2 of them. That leaves us with 5 for position 2 and then 4 for position 3. So this gives us 40 different arrangements, 4-letter arrangements with those restrictions. Number 4 says, in how many ways can a teacher seat 4 girls and 3 boys in a row of 7 seats if a boy must be seated at each end of the row? So we are placing all 7 students in this case. And there are 4 girls and 3 boys to select. However, a boy must be seated at each end of the row. So that's where our restrictions come in. The first and the last position must be a boy. There are 3 boys to choose from, which means you'd have 3 choices for that first seat. And then 2 for the last seat. Once a boy sits down, he can't be chosen again. We started with 7 students. We've used 2 of them. There are 5 left. And there's no restrictions on how those 5 can be arranged, which means there'd be 5 choices for seat 2, and then 4, 3, 2, and 1. And the fundamental counting principle says that we multiply these numbers together. 3 times 5 times 4 times 3 times 2. And you don't have to multiply by the 1, but we do have to multiply by that last 2. Gives us 720. So that's how many different ways those students can be sat if there must be a boy seated at the end of each row. Number 5, how many 5-digit numbers can we make using those digits if repetitions are allowed? So how many 5-digit numbers? So we're going to mark down 5 spaces. And it just so happens that there are 5 digits to choose from, right? But it doesn't have to be 5 digits. It can't, well, I guess it could be less than 5 because repetition is allowed. Okay? But you would have 5 choices for the first, and then 5 for the second because repetition is allowed. So that'll give us 5 to the power 5, which if you do that in your calculator, you'll get 3,125. So what if repetition is not allowed? Does that change the answer? Will there be more or less arrangements? Well, there's going to be less if repetition is not allowed. We'll mark down our 5 spaces. You'd have 5 choices for the first digit, but then only 4 for the second because repetition is not allowed, and so on. And if you do that one, there's 120. So again, there are fewer possibilities. That's what restrictions do. They usually reduce the number of things that can happen. So what we did in this last example is we went 5 times 4 times 3 times 2 times 1. That can be denoted by a 5 with an exclamation mark after it. And in math, that exclamation mark means factorial. 5 factorial means 5 times 4 times 3 times 2 times 1. And there's a factorial button on your calculator. So this will eliminate you having to go 5 times 4 times 3 times 2 times 1. The answer is 120, but here's how you get it on your calculator. You got to put the 5 in first. And then you go to math, which is below the alpha key. Hit the math key. Scroll across to probability. When you hit math, there's these different folders at the top. You're going to go to probability, and you see number 4 in this list is that exclamation mark. That's our factorial key. So choose number 4. There's 5 factorial in the calculator. Hit enter, and it does it. It goes 5 times 4 times 3 times 2 times 1. Okay? So in general, n factorial is n times the next factor is 1 less, so n minus 1. The next factor is 2 less than the first, n minus 2, all the way down to 3 times 2 times 1, where n is an element of natural numbers. And we're going to see that 0 factorial is actually 1, and we'll see why. But you can check it in your calculator. 0, math, over to probability, choose number 4. Your calculator tells you that 0 factorial is 1, but we will see why that is true. The arrangements of objects or people in a line is called a linear permutation. In a permutation, the order of the objects is important. When objects are distinguishable from one another, a new order creates a new permutation. So you need to remember this, that a permutation is an ordered arrangement. Order matters. You need to remember that. We're going to spend time talking about permutations where order matters, and then we're going to go on to combinations where order doesn't matter. So I'll give you a quick example of how they're different. Right? If you have people running for positions on the grad council, there's a president, a vice president, a treasurer, and a secretary. 4 different positions. Order matters. Getting selected for the president is different than getting selected for the vice president. Order matters. If, however, you have a committee to sit on the grad council and they all are just on the committee, they don't hold any special titles, they're all committee members, now order doesn't matter. Whether you're selected first or second doesn't matter. You're all on the same committee. Now, it's true the boys might have more power than the girls. I mean, that's just natural, right? Kind of the way it should be, right? But they all have the same title, so the order they're selected doesn't matter. So there's a difference between a permutation and a combination. So you're always going to want to ask yourself, when you get a question from this chapter, does order matter or not? If order matters, it's a permutation. If order doesn't matter, it's a combination. And the way you calculate your answer will change, depending on whether it's a permutation or a combination. But for the first, I think, 3 lessons, we're just going to be talking about permutations. Okay? So example 6 says evaluate each of the following without using a calculator. We'll use a calculator to check our answer, but we're going to evaluate without using a calculator. And here's how we would do this, right? 10 factorial means 10 times 9, and we could go on all the way down to 3 times 2 times 1. However, because the denominator is 8 factorial, I'm going to stop the top part by writing the last term or last factor as 8 factorial. See, this is equal to 10 factorial. 8 factorial means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Put the other 2 factors in front. 10 times 9 times 8 all the way down to 1 is 10 factorial. And the reason I stopped at 8 factorial is because that's a denominator. Now I have a factor of 8 factorial on both the top and the bottom. They cancel, and you're left with 10 times 9, which is 90. That's the value of 10 factorial over 8 factorial. And you could check that on the calculator by going 10 factorial divided by 8 factorial. You get that same answer. Question B, what about 7 factorial over 4 factorial? Well, 7 factorial is 7 times 6 times 5, and we could go all the way down to times 3 times 2 times 1, but I will stop at 4 and put a factorial on the end because that's the denominator, 4 factorial. And again, they will cancel. And you're left with 7 times 6 times 5. Well, let's do 6 times 5 first, which is 30, times 7 will be 210. That's what we should get for our answer when we go 7 factorial divided by 4 factorial in our calculator. So there's 7 factorial divided by 4 factorial. And we get our answer of 210. Okay. Now, normally it wouldn't make sense to do that when you're dealing with numbers like we did in this question, in this example. But we can use the same process for example 7, where it says simplify each of the following expressions. Because you can't put those in your calculator directly because there's variables involved. But we can simplify, which is what we're asked to do, by applying the same principle that we did above. The thing you have to know is which one should you expand. It's not always going to be the top that you expand. Sometimes it's the bottom that you expand. But if we look at what we expanded in each case, in example 6, it was always the larger number that expanded. Because as you go from factor to factor, it's always decreasing. It's always getting smaller by 1. So you're always going to expand the larger expression. N is always larger than n minus 3. So you're going to expand n factorial. So the first factor will be n, and then each factor is 1 less than the previous. The next one will be n minus 1, then n minus 2. And we could keep going forever. But we're going to stop at n minus 3, and like we did above, the last factor has a factorial on it because that's our denominator. Our denominator is n minus 3 factorial. And we can divide top and bottom by equal factors of n minus 3 factorial. And so we're left with n bracket n minus 1 bracket n minus 2. There's our simplified expression. And you could multiply those out if you wanted to. Not necessary, but you could. All right, so we'll do the same thing for question B. We need to expand either the top or the bottom so that we get a factor equal on both top and bottom. And remember, you always want to expand the larger expression, which is the top, n plus 4 factorial. So the first factor will be n plus 4, and each one is one less than the previous. So the next one will be n plus 3. If I look at the bottom, it's n plus 2 factorial, which means I'm going to stop after that last factor. And the last factor in the expansion always has a factorial on the end. And so the n plus 2 factorials will cancel. We can divide top and bottom by a factor of n plus 2 factorial, which leaves us with n plus 4, n plus 3. So there's that simplified expression. Example 8, there have been questions like this on diploma exams. And it would say solve algebraically, which means, again, you've got to show all your steps that you followed to get to the answer. So we're going to do the same thing that we did in those last two examples, where we're going to simplify. The top, n plus 2, is larger than the bottom, so that means I'm going to expand the top. The first term will be n plus 2. The next term will be 1 less, which is n plus 1, and it has a factorial on the end. And the reason I stop there is because that's what the bottom is. And so now the n plus 1 factorials cancel. And you're left with n plus 2, that must equal 6, so therefore n equals 4. And you could check that in the calculator. If you let n equal 4, this is our check, you're going to have 4 plus 2 factorial over 4 plus 1 factorial. That should equal 6. Which means you should have 6 factorial over 5 factorial. And 6 factorial is 6 times 5 factorial. The reason I stopped at the 5 factorial is because that's what the bottom is. The 5 factorials cancel, excuse me. Yeah. And it checks. We get the same expression on both sides. So we've just shown that our answer is correct. Now tomorrow we'll see examples like this where we're actually going to get a quadratic that we have to solve. So we'll see examples of those. Okay, but we'll stop there for now. So page 9 and 10, there's some questions to work on. I will post these solutions to Google Classroom so you can check your answers. Okay? But for now, you need to clear your desks so you have your calculator, pen, pencil, so you can write your Chapter 10 quiz.